Okay, so let's start with a bit of a nightmare scenario. Imagine you're dropped into a game. But here's the catch. There's no rule book
Yeah,
at all.
none.
There's no teacher standing over your shoulder, telling you, move that piece there or don't touch that. You just have to move. And after maybe 100 moves, a voice from the sky just yells, "You lose."
That sounds incredibly frustrating. And, I mean, it's also a pretty good description of how life feels most of the time.
Right. But it is also the absolute core problem of artificial intelligence, at least when we step away from just, processing data. How does an agent, a machine, learn what to do when there's no one there to correct every single move?
And that's what we're diving into today, this world of reinforcement learning.
It's one of the most exciting areas in AI, really.
Oh, absolutely. Because it moves us away from spoon-feeding computers information, we aren't giving them the answers. We're asking, how can machines learn from success and failure? From, well, reward and punishment.
So help me draw the line here. Most people, when they hear AI, they think supervised learning. How is this different?
Okay, so think of supervised learning like learning chess with a grandmaster sitting right next to you. You move a pawn, and they immediately go, nope, bad move. Move the knight instead.
You have a labeled data set, an answer key.
Exactly. You have the answer key. But with reinforcement learning,
You're all alone.
you're alone in the room. You're playing against a ghost. You might make 50 moves, some brilliant, some terrible, and it's only at the very end you get a signal, a reward.
A checkmate, or you just lose.
Right. And the problem, the really hard part, is that the agent has to figure out which of those 50 moves actually led to the win. It's called the credit assignment problem.
It reminds me of how a baby learns to crawl. I mean, there's no physics manual in the crib. They just wiggle.
They just wiggle, exactly. And if they move forward, that's a success. That's a little dopamine hit or reward. If they faceplant,
Pain, punishment.
yep. The agent, or the baby, is hardwired to recognize certain inputs as just good or bad.
So we have an agent, an environment, and a reward signal. To really get how this works, we need to strip away all the complexity for a second. Let's talk about the 4x3 world.
Ah, yes. This is the classic hello world of reinforcement learning. Just imagine a simple grid. 3 rows, 4 columns. The agent starts at the bottom left. The goal is to get to a specific square that gives it a reward.
And there are stakes, right? It's not just a casual walk.
Oh, high stakes for a tiny grid. There's one square with a reward of +1. That's the goal. There's another square with a reward of -1. That's the pit of doom.
Yeah.
But here's the little twist that makes it interesting. Every single step the agent takes costs something. Usually a tiny negative reward, like -0.04.
Wait, hold on. Why do you punish the agent just for moving around? That seems kind of harsh.
Well, you have to think of it like rent or the cost of energy. If moving was free, the agent might just wander in circles forever, being perfectly safe but never actually doing anything.
So the cost creates urgency.
Exactly. It forces the agent to find the shortest path to the +1.
Okay, so the agent's in the grid. It doesn't know the map, doesn't know where the +1 is. Where does it even begin to learn?
So we usually start with something called passive learning. Think of this as the agent being a passenger in a car. It's not steering, it's strategy, it's policy, it's fixed. It's just told, go northeast, northeast.
So its job isn't to decide, just to observe.
Right. It's trying to figure out the utility of where it is. It's asking, okay, is this a good spot to be standing in?
And there are 2 main ways it can figure this out. I think of them as the scientist method and the street smart method.
That's a great way to put it. The scientist method is called adaptive dynamic programming, or ADP. The agent walks around and basically builds a complete map, a model of the environment.
So it's memorizing the physics. If I drop this ball, it falls.
Precisely. And once it has that perfect map, it solves a massive set of equations to calculate the exact utility of every single square on the board.
That sounds exhausting.
It is computationally incredibly heavy. For a little 12-square grid, it's fine. For a game like backgammon, you'd be solving 10 to the power of 50 equations.
The universe would end before you finish the math.
Pretty much. So the scientist method is way too slow for the real world.
Okay, so what about the street smart method?
That's temporal-difference learning, or TD learning. With TD, the agent doesn't try to build a perfect map of the universe. It just looks at the difference between what it thought would happen and what actually happens, right now.
Can you give me an example?
Sure. Imagine you think your drive to work takes 20 minutes. But today, you hit traffic at one intersection, and it takes 30. The ADP scientist would try to recalculate the traffic physics for the entire city.
Which is impossible.
Right. But the TD Street Smart agent just says, okay, my estimate for this intersection was off. I'll nudge my expectation up a bit. Next time I'll guess 25 minutes. It just makes a local adjustment.
It learns from immediate experience without needing the whole picture.
Exactly. It's crude, but it's fast. And in AI, fast often beats perfect.
So far, though, our agent is just a tourist. To actually play the game, it needs to get off the sidelines and start making choices.
It needs to take the wheel. And this is where we shift to active learning. And immediately we run into a trap. The trap of the greedy agent.
I love that name. Sounds like a cartoon villain.
It kind of acts like one. So we switch the agent to driver mode. It has to choose where to go to get the most reward. And in early experiments, researchers made an agent that acted greedily, meaning at every single step, it looked at what it knew and chose the action that looked best right now.
That sounds logical, though. If I see $1 on the sidewalk, I'm going to pick it up. Why is that a problem?
Because what it knows is incomplete. In the experiment, the agent found a path to the +1 reward. But it was a long, roundabout path, the scenic route.
But it worked.
It worked, so the agent became greedy for that known reward and kept taking that same long path. It never bothered to check the other side of the board, where there was a much shorter, much faster path waiting.
So it settled. It found a mediocre job and just stopped trying to find anything better.
Exactly that. It stopped learning because it stopped exploring. And this is the fundamental dilemma in all of reinforcement learning. Exploration versus exploitation.
This applies to everything. Do I go to my favorite restaurant where I know the food is a solid 7 out of 10? That's exploitation.
Or you try that new place that just opened.
Which might be a 10, or it might give me food poisoning. That's exploration.
In math, we call this the multi-armed bandit problem, which is just an old-timey name for a slot machine.
Right. You're in Vegas, you pull a lever, it pays out $5. Do you keep pulling that lever forever?
Or do you try the machine next to it, which might hold the jackpot? If you only exploit, you miss out. If you only explore, you just waste all your money.
So how does an AI solve this?
Yeah.
It can't just wander randomly forever.
The solution is a strategy called GLIE. That's GLIE, greedy, in the limit of infinite exploration.
Okay, what does that mean in English?
It means you explore a ton at the beginning, like a teenager trying out different hobbies, and then slowly over time you become more greedy and focus on what you've learned actually works. But the trick is something called an exploration function.
This was the part about optimism in the face of uncertainty.
Yes. The agent assigns a higher sort of artificial value to places it hasn't visited much. It pretends that there are wonderful rewards hiding in the unknown.
So it's basically lying to itself. It tells itself, I bet that dark, scary cave is full of candy.
In a useful way. It forces the agent to go check it out. And if it goes there and finds, a pit of spikes, it updates the value and won't go back. But that initial optimism ensures it doesn't get stuck in a rut like the greedy agent.
That is surprisingly good life advice. Assume the unknown is good or you'll never leave your house.
It really is.
Okay, so I want to get to what I think is the biggest breakthrough in this whole field. We talked about learning the value of a state, like being in this square is good, but then there's Q learning.
Yeah.
And that changes everything.
It's a massive shift because instead of learning state A is good, Q learning learns taking action X while in state A is good. It learns the value of an action in a state. That's the Q function, Q of SA.
And why does that distinction matter so much?
Because it allows for model-free learning. Remember how our ADP agent needed to know the physics of the world?
Right, it needed the whole rule book of the universe.
A Q-learning agent doesn't need the rule book.
Yeah.
It doesn't need to know that gravity exists to learn how to catch a ball. It just learns. When ball comes high, raise hand equals success.
It bypasses understanding why the world works and just learns how to win.
That's the game changer. It means we can drop an AI into a complex, messy environment where we don't even understand all the rules and it can still figure things out.
And within this model-free world, there's a fun little debate between two algorithms, Q-learning and SARSA.
SARSA, state action reward state action.
Ouchie.
Very. Now, the technical difference is that Q-learning is off policy and SARSA is on policy, but that's just jargon. The best way to get it is the drunk friend analogy.
Okay, I'm ready.
Imagine you're walking along a cliff edge. There's a path right on the edge that's the fastest way home, and a safer, slower path further inland. Q-learning learns the absolute optimal path, assuming you walk perfectly.
So it would choose the cliff edge path.
It says, that's the highest value, go there. But SARSA SARSA learns based on what you actually do. If you have a policy that involves some randomness, like a drunk friend stumbling around, SARSA realizes, hey, walking on that cliff edge, there's a good chance I'm going to fall off.
So SARSA would learn that the safer path is actually better.
Exactly. Q learning is the idealist. If I were perfect, this is what I'd do. SARSA is the realist. Look, I know I'm a bit clumsy, so I'm staying away from the edge.
Okay, but so far we've been in this tiny 4x3 grid. The real world is massive. Backgammon has 10 to the power of 20 states. Chess, 10 to the 40. You can't make a spreadsheet that big.
You'd run out of memory on all the computers on Earth. This is where we hit the wall of what we call tabular methods. We need generalization. We need the agent to handle states it has never, ever seen before.
How does it do that?
Through something called function approximation. Instead of memorizing every single board position, the agent learns to look for features.
Like a checklist.
Totally. In chess, that checklist might be, do I have more pieces than my opponent? Is my king safe? Do I control the center of the board? And it uses a formula to weigh those features and come up with a score.
So even if it's in a position it's never seen, it can still estimate if it's winning.
It can generalize. It's basically mathematical intuition. And this leads us to one of the most famous stories in AI history, Arthur Samuel's checkers program.
This was back in 1959, right, when computers were the size of a room.
1959. And Samuel wasn't even a checkers champion. He couldn't teach it how to win. So instead, he just had it play against itself thousands and thousands of games.
Its own practice partner.
Exactly. And he used this function approximation. He let the AI figure out which features actually mattered, and eventually a human champion played against it, and the machine won. In 1962, it was the first time a computer learned a task to a level where it could beat the person who programmed it.
That must have been a bit of a shock in the 60s.
It was revolutionary. But it gets even crazier if we jump to 1992 with TD Gammon. This was a backgammon program that used a neural network and that TD learning we talked about.
And this wasn't just good for a computer, was it?
No, this thing was alien. It played 200,000 games against itself. And because it wasn't learning from human strategy books, it developed a style that was completely different from how humans had played backgammon for centuries.
There's that great quote about it from Kit Woolsey, who was a top player.
Yes. Woolsey saw the moves TD Gammon was making, and at first he thought, this is just garbage. No human would ever move there. But then he analyzed it, and he realized the AI was right.
It was better.
Its positional judgment was better than his. The AI had discovered strategic concepts that humans had just completely missed because we were stuck in our own traditions.
That's the real power of trial and error at scale. It doesn't just copy us, it can surpass us. But okay, well, board games are one thing. Let's talk about robotics.
Right. When you move to robots, you often shift focus from learning values to something called policy search. You just want to tweak the robot's rulebook directly until it stops falling over.
The classic example is the inverted pendulum, balancing a broomstick on your hand.
It's a classic physics problem. And as early as 1968, an algorithm learned to balance a real physical pole for over an hour.
But the coolest example, the one that really shows how far this has come, is the autonomous helicopter.
Oh, this is pure science fiction. Flying a helicopter is insanely difficult. Researchers at Stanford decided to use reinforcement learning to train a helicopter to fly itself.
But you can't just let a real helicopter learn from failure. That gets expensive.
Very expensive. Reward, -1, you just crashed $1 million machine. So they used a simulator. They crashed millions of times virtually. Then they uploaded that learned brain into a real RC helicopter. It flew. But not only did it fly, it performed maneuvers like the nose-in circle.
What does that even look like?
Imagine the helicopter flying sideways in a perfect circle with its nose always pointed at the center. It's incredibly disorienting and difficult for a human pilot. The AI nailed it. It learned the physics from the ground up, or I guess from the crash down.
It's amazing. We went from a tiny 4x3 grid where moving costs -0.04 all the way to a helicopter doing acrobatics.
It really shows the range. The core principle is the same. The agent interacts, gets a signal about success or failure, and adjusts. It's learning from interaction, not instruction.
Which brings us back to you, the listener. Why does this matter?
Because this is the closest AI gets to how we learn. It's natural learning. You touch a hot stove, you get a big negative reward, you update your policy, don't touch the stove.
But the text leaves us with this one really provocative thought at the end. It talks about the difficulty of reward shaping.
This is the final puzzle. For a grid world, the reward is easy. +1 for the goal. But for driving a car, What's the reward function? Don't crash is obvious, but what about don't be a jerk or drive smoothly?
You can't really write a math equation for good driving.
It's incredibly hard. So the suggestion is maybe you don't. Maybe we use apprenticeship learning. The robot just watches a human drive, and it tries to figure out what is the implicit reward function that human is following.
But wait a second, if a robot watches me drive,
I know where this is going.
it's going to learn that it's okay to go 10 over the speed limit if you're late. It's going to learn it's okay to yell at the guy who didn't use his blinker.
And that is the danger. Apprenticeship learning assumes the expert, the human, is rational and, good role model. If the AI learns our values by observing us, it's not just learning to drive.
It's learning our hypocrisy.
A mirror we might not really want to look into.
Yeah, and that is a deep dive for another day. Thanks for listening, everyone.
Keep exploring.